Hi, in this video we are going to talk about C++ library implementation of smart pointers. So there are mainly three smart pointers that are available in C++ library: unique PTR, shared PTR and weak PTR. Let's first understand unique PTR. All these three pointers are available in memory head file. So we need to include memory if we wish to use these smart pointers. So here is an example to demonstrate working of the unique PTR. We have a class test which has a member X. We have a constructor and a destructor. In the constructor, we have written constructor, cout constructor. Ideally, we should not be writing print statements in constructor and destructor. The purpose here is to explain the working only. So we have constructor, destructor, and then we have a function call. Inside the function call, we print the value of X. In the main function, we write main begins, and then we write this code inside these curly brackets. So they create a scope. Now when we create an object of PTR, we can either create it by passing a pointer, right? I have created a dynamically allocated object of test type and passed pointer to this, return pointer to this. The other way is using make unique function. Make unique function was added in C++ 14 version. So if you're using a compiler which is lower version or older version, make unique would not work. So in the older versions you can use this, but in the newer versions it is recommended to use this style. It's more readable and looks better. You create a unique pointer by simply calling make unique and passing the constructor parameters. And make unique is also a templated function like the unique pointer. In both unique pointer and make unique, we pass the data type for which we are creating the pointer. So here I created the pointer I created a smart pointer of unique pointer type by passing a pointer here. We could also replace this line with this line. After creating the pointer, we can treat it as a normal pointer. So I've called the function fun on this pointer using the arrow operator. I can use star operator, I can use arrow operator to access the members. So I use arrow operator, so fun is called. And the great thing is, since it is a smart pointer, not a normal pointer, the allocated object would be destroyed automatically. The destructor of class test would be called when you go out of the scope, right? So let's see the working of this program. What do we get as an output? The first thing that we get is main begins, because this is the first line of this main function. Then we are getting constructor because we are creating an object of test type here and we are passing the pointer of this created object to constructor of unique PTR. So we get the constructor output here. Then we call fun, so we get the output as 10 because fun simply prints the value of X. Now our object goes out of the scope. So when object goes out of the scope here, we get the output as destructor, right? And after destructor is printed, we have in the end main ends. So at the end we get the output as main ends. So this is how this unique pointer works, and this is how we get this output. Here is one more coding example of unique PTR to demonstrate the difference between unique PTR and other pointers. As the name suggests, unique PTR means if you have an object, ideally there should be only one unique PTR pointing to this. And that is the reason we cannot assign a unique pointer to other pointer, right? So the functions like copy constructor, assignment operator, they are not there in the unique pointer class. So if you try to do something like this, you will get compiler error. The reason for this is unique pointer works the way we have discussed our own smart pointer implementation in the previous C++ video. They are simple pointers. Once you create a unique pointer instance, and as soon as this instance goes out of the scope, it simply calls the destructor on that particular pointer. And if you have multiple other pointers pointing to that object, then there would be problems because the memory allocated by those pointers would be deleted. That's why unique pointers should always be used in a way that they point to one object and no other pointer or reference should be there for that particular object. And that's why they do not allow this copy constructor and assignment operator to be used in them. These functions are deleted inside the unique pointer class. The good thing about unique pointer is it causes very less overhead. It is a very simple pointer. You create a new unique pointer for a location. It constructs an object, and as soon as it goes out of the scope, it destructs the object. It does not maintain any other additional operation. If we talk about shared pointer allows multiple shared pointers to refer to the same location. And that is implemented by maintaining extra overhead like reference count to that particular location. In unique pointer, if you wish to transfer this object's ownership from PTR1 to PTR2, you don't want to maintain PTR1 to this location anymore and you want PTR to maintain this location, then there's a function called move. So assignment is not allowed, but we can call move function. So when you call move function, the ownership of the object from PTR1 is transferred to PTR2. Now PTR owns this object, right? And when PTR goes out of the scope, this object would be destructed. Let us now talk about shared pointers. Shared pointers allow multiple shared pointers to point to the same object. This is different from unique pointers. In unique pointers, one pointer owns an object and other unique pointers cannot co-own it. You transfer the ownership, but you can't have co-ownership. Shared pointers do have co-ownership. Let's see with this example. We have the same user-defined test class. We created first shared pointer PTR1. Please note that like unique pointers, we can create shared pointers two ways. One is directly passing a pointer to the constructor. Other is using make shared function. And this is a recommended way of doing it. This was added in C++14. Make shared and make unique both were added C++14. So this won't work in the earlier compilers, but this is better way of creating a shared pointer than this thing. So here we create a shared pointer PTR1. Then we have PTR2 equal to PTR1. Now what happens is you have one object, right, which has value 10, one object of test type which has value 10, and now two pointers PTR1 and PTR2 co-own it, right? These two shared pointers co-own it. And internally, shared pointers maintain how many shared pointers co-own this particular object. So they maintain a reference count, and there is a way to access this reference count. If you call ptr1.useCount, you will get the output as 2. Now if you call ptr2.useCount, you will again get the output as 2 because there are two pointers, two shared pointers pointing to this object. So we have co-ownership. Multiple shared pointers can own an object, and if all shared pointers go out of the scope, then your object is destructed, right? When the reference count becomes 0. So let's see the output of this one. We have created an object of test type here, so we'll get the output as constructor. Then we are assigning PTR2 to PTR1, so PTR2 start referring to or pointing to the same object. Then we print use count, so we get the output as 2. We again print the use count on PTR2, we get the output as 2. Now once the main function is over, they both go out of the scope, so we get destructor on the screen. Please take a closer look at this program and try to guess the output of it. This test class is same as we have been using. Inside this main function, we have created a shared PTR P1. We have not allocated an object for it. It's just declared, right? Now, we created a scope using curly brackets, and inside this scope, we created one more shared PTR variable P2. And we created using make shared, and this time we constructed an object with value 10. Now what we've done is P1 equal to P2. We have assigned P2 to P1. After this scope is over, P2 goes out of the scope, right? This pointer variable goes out of the scope. Then we print main ends and then we return 0. So what will be the output? The output of this program is constructor, main ends and destructor. So when you create an object of shared PTR, it does not create a test object because it's just declared here, right? And when you go inside this particular scope, this is where you create an object using make shared. This is the line because of which you get the output as constructor. Now you assign P1 to P2. So one object is being created here of test class, and now we have two shared pointers pointing to it. So its reference count is 2. Now this object P2 goes out of the scope, but you still have one reference count. That is why destructor is not called yet. So we get the output as main ends, and when we are about to come out of the main function, this P1 also goes out of the scope. So we get the output as destructor because then reference count becomes 0. Now say if I remove this line, I comment this line, what will be the output of this program? I remove this line, what do you get as an output? Your output would be constructor, destructor, and then main ends. This will be the new output of your program. Why are we getting this output now? What happens here is P1 is just declared here. We have just created, we have not bounded with an object. Now we create shared pointer P2. It's creating an object here, and reference count of this object is 1. Now P2 goes out of the scope, so reference count becomes 0. So we get the output as destructor because reference count is 0 for this object now. Now we come here and we print main ends. So we have talked about shared pointer, which allows multiple shared pointers to own an object, but it also involves overhead. So in general, if you can use a unique pointer, it's better to use the unique pointer than shared pointer because there is extra overhead involved for reference counting. Let us now talk about weak pointers. Weak pointers are used for shared pointer objects. So if you create an object with shared pointer, and if you have a shared pointer for that object, and if you don't want ownership of that object, if you don't want to increase reference count for that object, you can create one more weak pointer to that object. The purpose is sometimes you want to create some temporary pointers. You don't care whether the object pointed by them is deleted or not. You just want to create some temporary pointers and use them. You don't want to increase reference count when you are creating a temporary pointer. You use weak pointer for those purposes. Let's take a look at this example. It's the same test class. We have created a weak pointer P1. Now we have created a shared pointer P2 using the make shared. Please note that weak pointers do not have any function like make weak because they only bound to an existing object. They don't own any object. So you have some objects which are owned by a shared pointer. You just access the same object using weak pointer without increasing its reference count. That's the simple idea. So we create a shared pointer inside this scope created by curly brackets. Now what I've done is I've done P1 equal to P2. Now this P1 is a weak pointer which also has pointer to or reference to this object created by P2, which is owned by P2. Now what happens? What do you get as an output? This is interesting, and you now understand weak pointer. You may try guessing it yourself. So the output of this program is going to be like this. You have not created any object so far of test, so you won't get any constructor output. Here you create an object, so you are going to get the output as constructor. Now you create a weak pointer. So weak pointer does not increase reference count. So when you come out of the scope, what will happen? This object will be destructed here only as soon as you come out of the scope. Even if you have a weak pointer referring to that object or pointing to that object. So you are going to get destructor immediately after constructor. Then you come here and you are going to get the output as main ends. So this is what you get as an output. If it was a shared pointer, then we would have got constructor, main ends, and then destructor, because shared pointers increment the reference count, and weak pointers, you don't have to worry about them. If there are weak pointers, let them be there. You don't have the reference count for them, and you can deallocate the memory. So let's talk about some more things here. If I call here p1 dot use count is a function, what will I get as an output? Use count tells you the reference count, and p1 is a weak pointer, and you can call use count on a weak pointer as well. So you will get same output constructor, then you will get use count as 1 because there is only one reference count. Even if you call it on p2, you will get the reference count as 1. Then you will get destructor because there is only one reference count and this has been destructed, and then you will get main ends. Now one more thing, if a weak pointer is pointing to an object and if that object has been destructed, then there should be a way to check whether the object is valid or not. So for that purpose, weak pointer has a function called expired. So if you call here, let's remove this output as well. Now if I call here cout p1 dot expired, I'll get the output as true. Expired function returns true if the object has been deallocated, otherwise it returns false. So I'm going to get the output as 1. So C++ compiler is going to print 1 for true. So that's what is expired function. There is one more function which is supported by weak pointer, and the function is to upgrade it to a shared pointer. Suppose I created a temporary pointer and for some time I'm using it to do some computations, and I don't want the memory allocated to this temporary pointer to be deallocated during this time. So I can upgrade it to a shared pointer for that moment. So there's a function called lock which converts a weak pointer to a shared pointer. So I can create a shared pointer here. P3, and I can say lock P1. P1 is a weak pointer, and this lock function returns a shared pointer corresponding to the object which is being pointed by weak pointer P1. So weak pointers are used to create temporary pointers, and they are always used with shared pointers. They are used for the objects which are owned by a shared pointer. Weak pointers do not increase the reference count. We can upgrade a weak pointer to a shared pointer using lock function. We can also check if the object pointed by a weak pointer has been deallocated or not using expired function. Here is one more purpose that weak pointers serve. The purpose is the problem of cyclic dependency with shared pointers. Suppose you have two classes A and B, and you have two objects of one object of class A and one object of class B. And class A is designed in a way that it holds a shared pointer of class B's object, and class B is designed in a way that it holds a shared pointer of class A's object. So sp3 is the pointer inside the object of class A that holds address of this object, and sp4 is a pointer inside class B which holds address of this object. Now reference count for both the objects is 2, and we cannot delete any of the objects. If you delete this object, then you can't delete it because there is a reference count from here to here. And if you try to delete this object, you can't delete it because there is a reference count from here to here. There's a pointer sp3 which is pointing to this object. So reference count cannot be decreased to 0, and they both cannot be deleted. To solve this problem, we use weak pointers. We can have one pointer as a weak pointer rather than both of them having a shared pointer. And this reduces the reference count and solves this problem of cyclic dependency. In this video, we have talked about unique pointer, shared pointer, and weak pointer. These smart pointers avoid the headache of deallocating the memory, and they also remove the chances of memory leak. If we are a programmer, we might forget deallocating the memory, or we might write a program that in some flow does not deallocate the memory. Suppose you allocated the memory and some exception occurred, and in the cache block you forgot to write the delete block. Even if you have a delete code after the cache, so memory is not deallocated in those cases. So to handle all those problems, we can always use smart pointers. It's recommended to use smart pointers over normal pointers. And among all these 3 pointers, we should prefer to use unique pointer wherever possible, because it's a simple pointer, no extra overhead. And if unique pointer use is not possible, then we can use shared and weak pointers.